Okay, I am recording now. So this is the conclusion of the heating loads analysis with option 1 and option 2. We have the peak, we have to add here peak heating load and peak heating load 2. We have to do the same with cooling. Okay, we can do the same with cooling loads, but if we are analyzing the peak heating loads with option 1, we have this. This is the number. With option 2, we have this one. So what are the energy savings? The total energy savings is the first value minus the second value, and this is the total. But is it a significant saving? It depends. Then we have to turn that into money. We can do that later. But what is the percentage of savings? Well, we have to do this operation here. If 2,350 is 100% of the energy that we can consume, what percentage is 1,620? This is X percent. So this is 1,620 times 100 divided by 2,350. And this is 69% of the option 1, the savings. 100 minus 69, so it's 31%. Okay, that would be the conclusion for this analysis. So we have to quantify the savings of the heating loads and the cooling loads, option 1 and option 2, or first analysis or second analysis, and meeting the passive house standards. Then what's next? We can go to the economic analysis. We can do that, but we're not going to do it because we're not talking about money here yet. Probably, maybe we will talk about money, but not now. We want to save energy. Then saving energy means saving money, but that depends on a lot of things, a lot of factors that are out of our control, like the price of energy, if there are subsidies, if we have renewable energies. But this is the actual energy savings, and this is what matters from the building science point of view. Then we have to carry out an economic analysis, and probably what persuades our clients is the economic analysis, is the pay front and the revenue and all that stuff. But in building science, what matters is the savings, the energy savings. So this is the conclusion of this first heating and cooling loads analysis. Then we have to analyze the envelope, the thermal analysis of the envelope. And we have two software here, two tasks. We have to analyze the dew point analysis for wall, floor, and roof. And finally, the therm analysis. Okay, so you remember that we can use this software at the beginning. We have to prevent condensation risks. So here we have a risk of condensation because there's an intersection between these two lines. How can we solve this? We have to use air barriers and vapor barriers in the right position. So here inside the cellulose, remember that we have to insert a vapor barrier. The thermal conductivity is not relevant. The width, it has to be something very thin. And the vapor resistivity, it has to be something extremely high. So let's say 400,000. And if we do this, we can drag this down and drag this down. And it's not working. Probably because we have to do the same with everything here. Well, no, it's not working. Why? Oh, because we don't have this. There you go. Okay, apparently we haven't fixed it because of this. Okay, this is the vapor resistivity of plywood is not. So we have to go to the vapor resistivity of plywood, and it should be around 200. So this is not 200,000, it's just 200. Okay, if we do this, we can see that we have reduced this, but now we have this issue. And this is because, well, I have to fix it because it should be uh, a horizontal. Now, as of this point, this should be a horizontal line. Um well, I'll fix it because this is this is another version, so you don't have this version yet on Canvas because I have added something else, and apparently I screwed things up with this. Don't worry, I'll fix that. But anyway, the idea is that when we have an intersection here, we don't have an intersection, so we don't have condensation risks here. Here we do. So when we have these intersections, uh, first we have to add, well, first we need to change the properties of plywood. So here, even with this correct vapor vapor resistivity here, we have this, and then we need to add a vapor barrier. I think if we add here a large number, yeah, this is what should happen. Okay, I don't know. I have to look into this. So when this is solved, I will upload it in the on Canvas. But basically, we have an intersection. We have to add the vapor barrier inside the thermal insulation, and then this will happen, and we prevent this intersection from happening. And that means that there is not a risk of condensation under these circumstances, because we have stated here the indoor temperature, the outdoor temperature, relative humidity, outdoor relative humidity. But if these conditions change, we might have other risks. Okay, but at least we make sure that with these conditions, outdoor and indoor conditions, and this detail, we wouldn't have condensation. I'll fix this. So this is the first thing we have to do on this report. First, we have to analyze the dew point analysis of walls, floors, and roofs. Make sure that we don't have this intersection between the dry bulb temperature and the dew temperature. And finally, we need a therm analysis. We need a therm analysis at least of two options: the wall to roof and the floor to wall transition. Here you have a report, a sample. Okay. So first you have to analyze the building. We will analyze the building like this, at least 3D view and plan and sections, because I want to make sure that and highlight the spaces, because I want to make sure that the spaces are correctly placed here. We can have the orientation with the sun path. Okay. Do this again with Revit. You can analyze the R value of the walls with Revit with option 1 and option 2. So I have here all layers, and I have here the total thermal resistance, the R value. So the first option should be here, this is 27, that's fine. But the option 2, that should be, if this is the wall, that should be 50 or more. Okay, but you can do this with Revit. And then you have to copy the Revit loads analysis, and then you have to highlight the peak cooling and the peak heating load, because I want to check that the peak cooling load, the option 2 peak cooling and heating loads are lower than the first option. Okay, so you can copy this, but make sure that you highlight these elements so that I can be aware easily. And this is the second option. The R value is 50 or above. So in this case, R value is 50. And then here we have the second option. And if I look at this, peak heating and cooling loads should be lower on the second option than the first one. And this is the therm analysis. On this therm analysis, we need to, well, you have to copy the Revit detail and the therm analysis here, the Revit detail and the therm analysis here, at least for this wall to floor. And you have to do the same for the wall to roof transition. Okay. And this is what you have already done, or most of you have already submitted, the analysis with the Excel file and the analysis with Therm. And today we're going to explain the final points of this energy report. It's about ventilation, about passive heat gains through windows, and then we will analyze these peak heating loads and this monthly performance. This is what we are going to do today. And at the end, there should be conclusions. Okay. So we have 2 days to explain the rest of the assignment. You can download this. It's on Canvas. So you can load this sample report. And well, we need a cover page with your name on it and the title, the course, whatever, and the table of contents. And then you can start defining the building. We're going to do something like that. So we're going to place our building within, well, we have a couple of buildings here, but that will give us the, why don't we open windows to the east or the west? Well, we need to justify why we are not opening windows there, and it's because we have buildings or we have other buildings attached to that. Okay, so we have to provide a justification why we don't open windows on this. So we need to create like a site plan. So the first document will be a site plan. I will give you some hints, but it's up to you what you do with this site plan. Okay, let's get started with this. And I explained the ventilation loads, how you can calculate ventilation loads with this Excel file. Okay. So first, we need to apply a heat recovery. I told you that everything that it's above 50, it's good for a heat recovery. We need something like this. Okay, if we have an office building, we have an air handling unit on the top of the building, and then we can supply air, and then we can return the air to the heat recovery. And by having this heat recovery, we can increase the outdoor temperature from 0 to, let's say, 35. That would be a 50% efficient heat recovery. Okay, so we return this temperature or this air at 70 Fahrenheit. We have this 0 Fahrenheit airflow here, the fresh air, and then if it's a 50% kind of, the temperature here after the heat recovery would be 35. And then we need to heat up this temperature from 35 to 70. I do not heat up the temperature from 0 to 70 without a heat recovery with these schematics in which I don't recirculate the air to the heat recovery. I have to heat up air from 0 to 70. So a good way to save energy in ventilation is having this ductwork and having the heat recovery here. It comes at a price because if you remember systems, Then we need a supply ductwork and a return ductwork, and we have a lot of intersections, and we have to. So it's not easy. I mean, the concept is very easy. Okay, just create this ductwork and uh, yeah, create this heat recovery, and that's fine. That's the idea, the theory. That's easy. But then when it comes to the design, we have to figure out how to avoid intersections between supply and return ducts. And sometimes if spaces are very tight, that's difficult. Okay, but it's worth it because we save 50% of the ventilation energy, and that makes sense. So first, ventilation, and second, infiltration. So the best infiltration is the infiltration that doesn't exist. In a perfect world, we would have 0% of infiltration, but world is not perfect, so we have to assume that there are some mistakes or there are some flaws in the construction process, and well, there will be some infiltration, but we have to reduce this infiltration to the yeah, we have to reduce that infiltration. How can we calculate that? Well, I explained this last week, but I'm going to do it again. So first, the ventilation, we have to apply the heat recovery, the number of people, 20 CFM per person. 20 is 90% of buildings we can design. We will use 20 CFM per person, except if we have smoking rooms or gyms. So there are some exceptions, or hospitals, but in the 90% of buildings that we can design, we can use 20%, 20 CFM per person. We select the heat recovery, the number of people. We can fix this in 20. And then we have to apply the sensible heat and the latent heat formulas. And here we use the indoor and outdoor temperature. Here we use the wet bulb temperature. And the wet bulb temperature is something that we have calculated here with this Excel file by introducing relative humidity, indoor and outdoor temperature. We get the wet bulb here. Okay, so these two values are used here in the latent heat ventilation load. So this one is the CFM times 0.68 times wet bulb inside minus wet bulb outside. And the total is the sensible plus the latent heat. What about the infiltration? Well, for the infiltration, it's not something that we can calculate easily unless we have a blower door test. If we have a blower door test and we have this number, the air changes per hour at 50 pascals, and this is the outcome of the blower door test. Everything that is 3 or below, it means that the building is tight, so it's a good construction. If we made blower door tests in 90% of the buildings that we have in Kim, there will be a value that is higher than 5 or 7, because well, construction 50 or 60 years ago, it wasn't as good as it is now. And in addition, they didn't have the standards. Okay, so it's not that the construction was not good enough. It is because they didn't work with the standards, with restrictive standards that we are working now. Okay, so if you are going to refurbish a building, or if you are hired to design an energy retrofit of a building, the first thing you should do is to carry out a blower door test. This is not easy because the equipment is quite expensive. Okay, but at least with that test, we know if we have troubles with infiltration or we don't, because no, probably it's a good construction. I don't know, maybe it's a quite good company that constructed this 50 or 60 years ago, and and it's fine. But this is the first thing we should do, and we should have this number. So if this number is below 3, that's fine. If it's from 3 to 5, well, it's not bad. If it's above 5, we have to do something seriously against this infiltration. But we can't know this number without a test. If we have a test and we have 3, with 3, most likely we will meet these passive house standards. And then this n, remember that depended on 2 factors. That n value depended on the zone. Okay, so we have this chart and this map. It comes from the ARCH360. Okay, we can rely on that source. This ARCH360 62.2. So first we need to understand where what zone we're in. This white one is. It doesn't depend on the temperature. It depends on the wind speed or wind velocity. Okay, so it doesn't depend on. It's not that Florida is in because here Texas is in zone 2, the same zone as New Hampshire. Probably because in this alley here, we have the same amount of wind or the same speed of wind. Here we have more, and well, the 1 is the worst. The 4 is the best, the more exposed to the wind. The 1 is the area that it's more exposed to high speed winds, and 4 is the one that is less exposed to that. Anyway, that comes from ARCH360. Here we have the zone. If in New Hampshire we are zone 2, and then we have the well-shielded building, normal building, or exposed building. I told you that well-shielded is a building that it's if there are buildings attached to each other, those are shielded because they are not exposed to wind at 4 sides. So this is a well-shielded building. If we are surrounded by trees or other buildings around, we can have a normal, and it is exposed. If we are at the top of a mountain without any trees, without anything around, it's completely exposed in 4 directions. Okay, I would use normal unless if we're working in a building that is attached to other buildings, it will be well shielded. If it's exposed, that would be in the middle of nowhere at the top of a highest mountain. So I would use normal. Okay, so 80% of the cases will be normal for detached single family houses or detached buildings. And in normal, this is the number of stories. We can have 1, 2, or 3 or more. If it's a 1 or 2 story building, that's why I used 14.8. If it's 1, it's more exposed. Well, in the building we are analyzing, I was using this one because here we have a 2-story building, but in the building that we are analyzing with Revit is a 1-story building. So that should be 18.5. Okay, if I use here 18.5, it's a 1-story building, and well, it's actually it's less exposed. The taller the building, the more the wind exposure. Okay, so it's less exposed. Okay, so you see that when it's well shielded, this number is higher. Okay, so the higher the number, the less the wind exposure. So 18.5, it's better than 14.8. Okay, so it makes sense. If we have a 1-story building, it's less exposed. So the higher the building, the more facades and the more the exposure. Okay, so once we're done this, we have the results of the blower door test, we have the exposure, the wind exposure, and then we have the volume of the building. And the volume of the building is the area times the height of the building. With this, we turn air changes per hour into CFM, and I explain how to do that here. Here, okay? So that depends on the volume of the building. Here you have the air changes per hour, and basically you have to divide the volume times 60. So one air change per hour is the volume divided by 16, and that's it, okay? And this is what we have done in this. So this is the air changes per hour, but the real ones, not the one that comes from the blower door test. Okay, so this number is 3 divided by n, by 18, and this CFM is this number divided by 60. Well, this number times the volume divided by 60. Okay, so here with these parameters, so if you do this with the passive house standards, you can type 3 because 3 is a good value, 2 is better, 1 is even better, and 0 would be the best. Okay, but we can't have 0, but I mean 3 it's good for starting analyzing this. Okay, so let's start with 3. And with this, we can calculate the sensible and the latent heat again. We have the same formulas, but now we have this CFM. We don't have the CFM that we had here, depending on this number of people. We have the CFM that depends on the infiltration rate. So that will be 1.1 times the CFM times indoor minus outdoor temperature, and that would be 0.68 times the CFM times indoor minus outdoor wet bulb temperature. And this is it. And now we can calculate this ratio would be, I think it will be good. The ratio between ventilation and infiltration. Okay, it's something that we can see here in this graphic. This is the ventilation load, and this is the infiltration load. If infiltration is less than 10% of the ventilation load, that would work well. So another thing that we can analyze here is the ventilation load and the infiltration load. Ventilation was 17,655. 17,655 BTU hour, and infiltration 4,490. Okay, so now what is the ratio between now we are not talking about energy savings, we are talking about the ratio between infiltration and ventilation load. So if this is 100%, 17,655, what is the percentage of this value? The 4,490. It's the same, this times 100 divided by this. So let's do it. 4,490 times 100 divided by 17,655. Okay, so this is 25%. Option 2 is, okay, now infiltration. of ventilation. Um, well, that's I told you that 10%. It's I'm changing my mind now, because 10% would be a good number if we don't have a heat recovery. Okay, so imagine that we don't have a heat recovery, and now this is 35 and this is 4. So probably we are closer to 10% now. But if we do have a heat recovery, that means that we have increased the efficiency of our ventilation system. So even though if we have a good infiltration rate, I mean, we have 3, that means that we meet the passive house standards, that will be above this. Okay, so when I was a student, they told me the 10% infiltration rate compared to the ventilation, uh, because we didn't apply heat recoveries. So we were looking for air tightness. Okay, so now I don't. What do you have to do? You have to reduce this. A 50% heat recovery is good, but a 70% heat recovery is better. And then you have to reduce the infiltration rate. If we have a blower door test and this is 2, there's nothing we can do. And this 2,900, it's more than 10% of 10,000. But we can't improve this any further, because more than 70% energy heat recovery efficiency. Yeah, we can have 80, 90, but it's very unlikely. 70% is quite good. And less than 2 air changes per hour for the blower door test. Again, it's something very difficult to achieve. Okay, so with these 2 values, I'm happy. So I'm not concerned about this ratio between infiltration and ventilation. Anyway, it's something that probably we will be asked. Okay, so what is the ratio between infiltration and ventilation? The ratio is not important as long as we have reduced this as much as possible. Anyway, if you're asked to calculate the ratio between infiltration and ventilation, this is the way to do it. Okay, so now we have calculated ventilation and infiltration loads. You can use this number, 70% for the heat recovery efficiency, between 2 to 3 for the blower door test outcome. 2 to 3, it's quite a good number. And then you have to select the right number of people. This is always 20, and the right volume for your building. Okay, so it's not always 17, and this is not always 16,000. Okay, so we have evaluated with this Excel file if we have the right R value here. So for the wall here we have 45. We can increase that and we can make it 50 or above 50. For the roof, it should be above 70. So this is not enough now. Okay, so we can make it from 70 to 80. That will be good. And then for the floor, well, in this example is the only one that meets the requirement. It has to be 35 or above 30. So 35 is fine. When we have this, we can evaluate the heating loads that we have through the wall, through the roof, and through the floor. Well, here we don't have anything in the floor because, yeah, we don't have floor area. So the floor area and the roof area usually are the same. So let's say that it's okay. So now there will be a floor. Yeah. And then we have the ventilation, the infiltration, and this is the windows transmittance. So let's talk about windows now. Okay, we have this table here to evaluate the heating loads through windows. And we have explained that before, but we have always three different parameters in windows. We have the U value of the window. In walls, we are using the R value, but in windows, we are not using the R value. We usually find in catalogs the U value. This is not something that we can calculate. It's something that we have to get from catalogs. And okay, I can upload a catalog here. I can. Yeah, so I have this Guardian glass. I'm always using this Guardian. Well, it's a good catalog. But this is an information that we have to find on the internet, or we have to talk to the provider. Well, here we have this. We have the difference between single, double, triple, laminated glass. A laminated glass is not a double or triple glazing. A laminated glass is glass that we have a glue. It's not glue, but it's something that sticks two glass panes to each other. This can be transparent, or it can be with can come with a color. Okay, but this is the laminated glass. This is for safety. Usually we have this in banks, because by having different layers of glass glued together, then they are bulletproof glasses. We have this in cars as well. Do we have this in construction? When we have a glass handrail, usually is a laminated glass, because we have to provide this handrail with more resistance to impacts. And okay, so this is something that we can use. Or when we have a window shop, a window shop, those usually are laminated glass, especially if they are on the first floor, and we can have issues, or even if we have if we are in a curtain wall, we usually have laminated glass, because if something is wrong and the glass falls to the street, you can kill someone. Okay, so the laminated glass is something that provides safety, and that means that they are glued to each other, so parts of the glass are not falling down. Okay. Anyway, that's the difference between the double glass and the laminated glass. Here we have a double laminated glass. Okay, so double means that we have an air chamber, and laminated means that we have different glass panes stick together with this layer here, this sticky. The name of this is polyvinyl butyral. It's polyvinyl butyral. This is a clear resin polymer, and this is very strong adhesive. Yeah, so this is it. Okay, so we have two glass panes, and we have this film, and that sticks to two different glasses together. It can be transparent, or it can have a color. But this is the right material, the PVP. We were looking at the glass catalog. And yeah, and this is what we have. This is the kind of information that we have to look at. Here, again, it's overwhelming. We have a lot of elements. When we have ultra clear, that means that it's completely transparent. And we can show this with the visible light transmittance. Okay, so this number is the ability to transmit light. So with this number means that 64% of the light, visible light, we're not talking about heat, we are talking about light, goes through the glass. With this one, only 31%. So imagine that sunglasses are usually less than 30% of visible light transmittance. In what do we need in construction? Well, if we need natural light, we need to increase the visible transmittance. But sometimes in high-rise buildings, especially, we don't see this kind of ultra clear glass. We see this because we have a large amount of glass, so probably we don't need a completely transparent building or transparent glass. It depends, okay? And here we have different colors, can be gray, blue. We can achieve this lack of transparency with this layer, or it can be in the glass. We can tint the glass. The glass is not transparent. We can use a color when we're manufacturing the glass itself. We can use a color here, or we can create a layer that it's not transparent. It depends. What can I show you here? Well, this is a building, I know, and that's the effect. Okay, if we are using this kind of colored layers, this is the effect that we can have. It's cool, it's nice. Okay, we can use white, or there are panels that are transparent here. The first floor panels are transparent, but those have this color. Okay, but by using these kind of elements, okay, so that's the difference between the transparent glass and the non-transparent one. And I was looking for interior views of this building. Yeah, this is a museum, but do we have? No, we don't. I mean, those are not completely opaque, so you can see through these glasses. If we were looking at an indoor view of this building, we would see that we can see through the glasses, but it's not 100% transparent. Anyway, I can't find a picture right now. But that's the effect of this polyvinyl butyral glass. Okay. And how can we quantify this effect? By looking at this visible light transmittance. So the lower this value, the less transparent the glass is. So this is the first thing that we have to look at. Then we can look at the U value. The U value, we have a double glazing or triple glazing. We can have air or argon. Air is cheaper. Argon is much more expensive. It reduces the U value, and this is what we want. Okay, so we want to reduce this U value from 0.29 to 0.24. Okay, that's fine. And finally, we have the solar heat gain coefficient. And the solar heat gain coefficient is the amount of heat. It's not the visible light. It's the amount of heat that goes through the window. Okay, so there are three things that we have to look at when we are studying a glass: the U value, the solar heat gain coefficient, and finally the visible light. Visible light is if we are carrying out a lighting study, we need this parameter. We are not doing this in this course because we don't have time. And we are working with the U value and the solar heat gain coefficient. So what do we want? We want to reduce the U value as much as possible. Okay, so 0.29 is good. It's not bad, but 0.24 is better. And do we have anything else here? We have to go to a triple glazing. Yeah, okay. This is a triple glazing. So now the triple glazing is 0.21 with air and 0.18 with argon. We can, this is better. This is 0.12, 0.13, 0.12. Yeah, I think it's quite difficult having something less than 0.12 in glasses, with even with triple glazing, low emissivity coatings. It's quite complicated. Okay, so that would be the best in terms of heat losses. If we want to reduce the heat losses, we can use this one because it's the best one. What about the solar heat gain coefficient? Well, this is the ability of the glass to allow or to let solar heat enter the building. And now we have to analyze what we are doing when, where we are working and what kind of building we are designing. If we are in a cold area, I would increase the solar heat gain coefficient, because when the sun hits on the glass, a large amount of glass is entering the building. So 0.24 is too low. Only 24% of the heat enters the building. That would be great in a hot country or in summer. In summer, we want the other way around. We want to reject most of the heat that hits the glass pane. Okay, so that would be a good value in summer or in a very hot country or warm country. But in New England, I wouldn't use such a low solar heat gain coefficient. Okay, so in this catalog, yeah, 0.36 it's slightly better. This is the ultra clear. And what is this is 0.8. Yeah, but if we want to reduce the U value, 0.12, what is the best option in this list? That would be the best option because it has a very low U value and it has the highest solar heat gain coefficient. But it's always tough. This is a tough decision. And there is not a straightforward answer. This is the class that you have to use. What about the visible light transmittance? That would be 55%. Well, that's good. 59 is better. It depends on what we want. What matters here? Do we want visible light? Because we need natural light, because by having a lot of natural light, we can save money or energy in artificial light. So that matters. What is the savings in artificial light compared to the heating and cooling loads? Okay, this is something that we have to study. And but what if in a winter day we have sun and we have a very low solar heat gain coefficient? What if we have something like yeah, what if we have something like this? Here, this is 0.26, the U value, but the solar heat gain coefficient is 0.67. We're going to use two options, okay? We're going to use this one, the U value. We call this a glass selection. So we have two options. Option one, U value is 0.26, and solar heat gain coefficient is 0.67. And option two, U value is the lowest U value we have found. I think it was the triple glazing. Yeah. And the, okay, 0.12. The U value is 0.12 and the solar heat gain coefficient, it's 0.33. Okay. And now let's analyze these two options. So we have this chart here, this table, and what is the U value of the window? Let's select option one. I think option one was 0.26 and 0.67. Okay, so this is 0.26, the U value, and the solar heat gain coefficient is 0.67. What is the area of the window? Well, let's say that it's 100 square feet. We have north, we have south, 0.26. Let's say that we have 100, and this is 0.67. And we don't have the east and west, so the area is 0. Okay. So with this U value of window, this is the thermal load through the window. So the thermal load through the windows is the U value times the area times indoor minus outdoor temperature. So this is 3174. This is the heating load. For option one, heating load. Option one was 3174. 3174 BTU hour. What is option two? Let's find out later, because now I want passive solar heat gains. And this is option one and option two as well. So I have to compare these two options, option one, option two, and I have to compare heating loads and passive solar heat gains. I know that the lower the U value, the lower the heating load. And yeah, so that would be better in terms of heating load. But in terms of solar heat gains, this one is better than that one. So if I want to find the balance, how can we compare this and that? With this Excel file, we can do it. So here we have the heating load, and the other one is 0.12, 0.12, and 0.12. So by doing this, this is 1,488. BTU hour. Okay, now what is the energy savings, or what is the percentage of savings? We can do that again with this. Okay, but option one, option two, heating loads. But what about the passive solar heat gains? Well, the passive solar heat gain, it's something that we cannot do using power. We have to do this using energy. Okay. So heating loads, we are talking about power. But to analyze the solar heat gains, well, we have to analyze energy. We can use energy here as well. Okay, so that's why it's very important. You have to work with these two concepts: the power and the energy. We have to work with these two concepts. So when we are talking about BTU hour, this is power. If we are talking about energy, it would be only BTUs. So we have to multiply this times time. How much time? Well, it can be a day, or it can be a month, or it can be a year. So we need to set the time in which we are analyzing the energy balance. Power is at this point, at this very moment. Okay, now with these conditions, I have 70 degrees inside. I have 0 Fahrenheit outside. I have this window. So I'm losing this right now. I'm losing this power. This is the heating load. But what about energy? Okay, so how much time I am losing this power? I'm losing this power for 10 hours. Then I have to multiply this times 10. And that's it. And what about the passive solar heat gains? It's the same. So at this point, when we have a sunny day and we have a south window and the sun is hitting on that window, I have this heat gain. But what if it's cloudy? What if it's in the evening and we don't have any sun? So that's why we need to turn this into energy, because to understand this balance, power is not enough. Because usually for the heating loads in winter, the temperature is low throughout the day. And we can have 0 Fahrenheit now and -5 at 3 a.m. But what about the sun? The sun changes a lot, okay? Because now if it's at noon and a sunny day, we have a lot of energy, but in the evening I have 0. Okay, so that's why we need at least the daily balance or a monthly balance in winter and the monthly balance in summer. This is what I want to explain you today with this. Okay, so here we're analyzing the first option. The first option was 0.26. And the solar heat gain coefficient. And here we have the area of the window, the U value, solar heat gain coefficient, area of the window, U value, solar heat gain coefficient, and the area of the window. And this is the north and the south. And we need this table now. Okay, so in this table, we have the wall, the floor, the roof, the ventilation, and infiltration. Okay, so here we have all the components of the heating and cooling loads in a building. But now we are looking at windows transmittance and windows solar heat gains. Okay, so these are the two values that I want to compare. And I want to compare that in January. Okay, because in January, the windows transmittance is the heat loss and the windows solar heat gain is the heat gain. So if I make that the solar heat gains are higher than the heat losses, the balance in our windows, it's a positive balance. Okay. I'm going to explain this using a drawing. Okay, this is the building, and in the south facade, we have a window, and then I have the sun here. This is the sun. Well, the sun is yellow. Yep. And I can use gradient, and I can use well, let's do this. So this is the outdoor sun. So we have an energy, and we call that irradiance. Units of the irradiance, BTU, hour, feet square. There's a solar heat gain coefficient here in the window. we have the solar heat gain coefficient. In this case, it was 0.6. 0.67. Okay, so this is the solar heat gain coefficient of my window. So what is the total solar heat gain? Passive solar heat gains equals the radians in BTU hour feet square times the area of the window feet square times hours of sun. How many hours of sun? Well, it depends. How many hours a day do we have sun in January? Well, it depends. Yesterday we didn't have any. I think it was cloudy. Today we have a nice sunny day. So it depends. So what about this? We need to find data about the hours of sun. But this is the passive solar heat gain. And then on the other hand, in this we have 70 Fahrenheit inside, and there will be 0 Fahrenheit outside. Okay, so we have sun, we have this, but now we are losing heat. We are losing heat through the window. How much heat are we losing? And we will turn this into red. So this is the heat loss. Heat loss equals the U value times the area times 70 minus 0, indoor minus outdoor temperature. Is this enough? Well, it depends. Are we talking about energy or are we talking about power? This is power. If we are talking about energy, we have to multiply this times operating hours. Okay, and this is something that we have to clarify now. These are the hours of sun, and these are the operating hours. If the building is working 24/7, and if we're analyzing this in a single day, that would be 24. And if it was a cloudy day as yesterday, that would be 0. Okay, so these hours are not the same. The hours that we use for the solar heat gain are not the same as the hours that we use for the heating loss. So this has to be with the schedule of the building, with the operating hours. If the building is working from 9 a.m. to 5 p.m., so that will be 9, 10, 11, 12, I don't know, 7, 8, whatever. And if we have a sunny day and it's sunny from 9 to 5 p.m., so then the number of hours is the same, but the operating hours are always the same. The hours of sun are different depending on the day. So that's why doing this on a daily basis, it's well, what day? Are we studying a sunny day or are we studying a cloudy day? If we are studying a cloudy day, the balance is always negative. We are losing much more heat than we are gaining. Okay, so in a cloudy day, this is a sunny day. That would be a cloudy. So in a cloudy day, that would be almost nothing. It's not zero because we have always a diffuse light. So even in a cloudy day, we are gaining something. Okay, but that doesn't depend on the solar heat gain coefficient. It depends on the clouds. So let's make it. Do we have a cloud here? No, we don't. Okay. So this is a cloudy day, a little amount of energy. So in this case, the balance is always negative. This arrow is the same because this arrow depends only on the indoor and outdoor conditions. But this depends on two things. Depends on the solar heat gain coefficient, and it depends on the outdoor conditions, if it's sunny or cloudy. Okay, so on a cloudy day, the balance, we will always have a negative balance. But what happens on a sunny day? This is what we have to find out. And we can't do this just on a daily basis. We have to do this on a monthly basis because, okay, what is the average days in January with sun in Keene or in New England? Depends. That's why we have to do this on a, doing this on a daily basis. Okay, today, this is a perfect day. We have sun, 24 hours, no clouds. So today, the balance is positive. Okay, so how many days like that do we have in January? Only 2. Okay, is it worth it? What if it falls in the weekend and the building is not operating? So that's why we need to do this on a monthly basis. And this is what this Excel file is doing. Okay, so as you can see here, we have January, February, March. So we can do this. Let's stick to January because this is what we want to analyze today. And here we have the operating days per week, and here we have the operating hours per day. Okay. So if we select here, operating days per week is 5, and operating hours per day is 8. So this is the typical schedule of an office building. Okay. And how does it change? Well, that affects the times for, okay, so that affects, this is the number of hours that we are considering in our building. Why 177.2? Okay. How many hours per week? If we have 5 days per week and 8 hours per day, so that would be 40 hours per week. So how many weeks do we have in January? 4 weeks is 28 days, but in January we have 31 days, if I'm not wrong. Yes, in January we have 31. Yeah, it's here. It's 31 days. So what is this? Well, I have multiplied this times 4.43, because 3 days it's like 0.43. Yeah, it's 3 days, it's 0.43 weeks, something like that. In February, this is 4, because in February we have 28 days and there are 4 weeks. Okay, so when we have 31, I have multiplied this by 4.43, and if we have 30 days, I have multiplied this by 4.28. Okay, so that's the explanation. This is the number of hours that the building is operating. If we change this, if we change 724, now we increase the number of hours, okay, because it's operating every day. Basically, we will have 31 days operating the building. Okay, but if we have an office building that is working only 5 days per week and 8 hours, let's say 10 hours per day, so this is the number of hours that the building is operating. And what is the Windows transmittance? The Windows transmittance is this. And we do have, this is the U value. Well, it's this formula. Is the U value times the area of the windows times 70 minus 0 times the operating hours. Okay, so this is the energy. In this case, I have, where I'm doing this with this window, this is the U value of the window, this is the area of the window, the U value of the window and the area of the window. And the total value is 771,000, okay, 771,706. BTUs. The other way around, BTU. And the hours of sun, it's here, is 221.5. No, sorry. It's here because I'm calculating the heat loss. And the operating hours here is 2 to 1.5. Okay, so this arrow is 771,706 BTUs. We are talking about energy because I have multiplied these times the number of hours. Now, what is the value of this arrow here of the passive solar heat gains? We need to know the irradiance. That depends on where the building is set. It depends on the area of window. We have the area of windows because I have set the area of windows here, 100 in the south, 100 in the north, and Now, what are the hours of sun? And now we are not doing this in a day. We are doing this in January. Okay, so where can I find this? I need another software. Unfortunately, this Excel file cannot do that. So what software are we going to use? I think you have to become quite familiar with this PV watts, because we have used this in different courses, and it's quite good. It's for free, and it comes from the Department of Energy of the United States, so we can rely on that software. And now we need to insert our location here. So if our location is Keene, New Hampshire, yep, this is Keene, and this is to calculate PV panels. We are going to use this when we're running a PV panel analysis. But today, what I want is to analyze the solar heat gains. Okay, so we need only these two elements. Here we have the azimuth and we have the tilt. If we are analyzing windows, the tilt is 90. Okay, if we have a flat roof, that angle would be 0. If we have a vertical element, that angle would be 90. And then the azimuth, if you click here, if we're analyzing the south elevation, it's 180. And if we're analyzing the north elevation, that would be 0. Okay. So let's do it. If it's 180, it's the it's a window, it's a vertical window. No, it's a southern, and if we are typing here 90, it's a vertical window. Okay, the azimuth is the orientation, so this is south. The tilt is the angle, so 90 is a vertical, if I'm not wrong. Yeah. Okay, so 45 degrees, it's 12 by 12, so vertical is 90. Now I can analyze this. And the value I need is the solar radiation in kilowatt hours square meter per day. Okay, so I need this value. We are analyzing January. So this value would be 3.82. What do I have to do with this? Okay, so look at this. Here we have the south elevation because I'm analyzing the south elevation. And this here, here I have the instructions, enter data from PV watts in kilowatt hour square meter day. So this is kilowatt hour square meter day. So we have to do this in every single month, but we are analyzing only January. So that would be only January. So we're typing here 3.82. This is the south. What about the north? I can go back here and then I can change the azimuth. So north was 0. I type 0. Go back to the analysis. And look at this, the solar heat gains in the northern facade, it's 0.52. It's almost nothing, but well, it's something. So in the north elevation, it would be 0.52. We don't have east and west. So now with this, I turn these numbers into BTU hour feet square, because these values, I told you that everything that is used to calculate electricity, it has to be in international units. And this is meant to calculate the electric energy that we are generating with this. So that's why we are, even the Department of Energy of the United States is using international units. If we're using BTU and BTU hours, then we have to turn this into, and I have done this with all these operations here. And here, this is the total BTU per day. Okay, so here we have the total BTU per day that now we have to calculate in this chart. Since we have 31 days, we can calculate the total BTU per month. So what is the window solar heat gain here? The window solar heat gain in January, we have to multiply this times 31 days, and we have to add up the values that we have in this table. Okay, so this is 11,000, this is 81,000, and all these. So in this case, this number is 2,857,000. So what do you think? Are you still there?
Yep.
Okay, so Matthew, thank you for letting me know that you are there. Is it a good balance, or is it a positive or negative, or what do you think here?
I think for the month of January, it'd be kind of good.
I think so. Yeah, it's positive because we are losing 700,000 and we are gaining 2 million. Okay, that's the outcome of this exercise. And when someone tells you, okay, do not use Windows because well, do not use Windows. Come on. Let's analyze in probably in other places or with a different orientation, this balance would be different. But with the window that we have selected and the place which we have analyzed, it's in Keene, New Hampshire. In maybe in Alaska, that would be different, or in Minnesota, or in Chicago. I don't know. But in Keene, New Hampshire, if we analyze this, the balance between heat losses and heat gains, in this case, with this orientation and with this amount of windows, the balance is positive. That's the only thing that we can say. So it's not no, don't use a lot of windows because it's not working. Let's change this. So let's change now the solar heat gain coefficient, because you remember that we had the second solar heat gain coefficient, 0.33. So if we change the solar heat gain coefficient here, it's 0.33 and 0.33. What is the balance now? Well, it's not that positive because now we have 1 million. We used to have 2 millions, but now we have 1 million BTUs. Okay, it's positive, but it's getting worse. So depending on what kind of glass we select, the amount of the area, the orientation. So it depends, but we need data, and I think this is something easy, and we can use this to analyze. Okay, am I doing something good, or am I doing something that it's nonsense? Well, it's not bad. And opening windows to the south, well, it's always something that works. I mean, we need to quantify that. And yeah, sure, and maybe it will work someplace and it won't work in a different place. But opening windows to the south, usually it works in cold areas in which we have a lot of, because in New Hampshire, I think, well, we have a lot of sunny days, so we have a lot of hours of sun. Well, so that's the balance. What do you have to do now? Well, you have to go to your Revit file. Well, first in the report, if we're analyzing this report, let's open the file first. And let's work with the midterm. Okay, this is the midterm sample report that I posted on Canvas. Yep. So here you have to analyze you have to let me know what kind of glass you are using. It doesn't have to be this. So try different glasses, and then you have to select this to insert these passive heat gains through windows. And at the end, we need this graphic. Okay, so this graphic is comprehensive because we can analyze what happens in every single month. Okay, and that works in summer. But what happens in July? So we agreed that no, that works in January, sorry. But what happens in July? We agreed that if we didn't change, so with a 0.67 solar heat gain coefficient, the balance in January, it's good. It's positive. What happens in July? Okay, in July we have to go to PV watts again, and in July we have this number is 1.85. Okay, so in July we have to type here, no, here 1.85. So what happens in July is that we can have a lot of, where's July? Here. So in July, we have solar heat gains, and it is 2,436,000 with this solar heat gain. If we had a different solar heat gain, 3.3 in July, we would reduce this. So this is only 1,100,000. Okay, so what works in winter, it doesn't work in summer, because in winter we need to maximize the solar heat gains. In July, we have to minimize solar heat gains. So it's not that simple. It's not that, okay, in January it works well, but now what happens throughout the year? So that's why we need this balance. So eventually you have to type all these values that come from PV watts, okay, January, February, up to December. You have to type all these values here, and then we have to run the yearly analysis, because what works in summer doesn't work in winter, and the other way around. Okay, so the answer, okay, shall I use this glass? A simple answer like no, don't use glass in cold countries. Why? No, let's okay, what about the January balance? Okay, let's oh in January it's positive. What about in July? Oh, in July it's negative. So what can I do? I don't know. Now you have to decide what kind of building. Maybe you have holidays in July, and in July the building is not operating. Okay, that's fine. So July isn't the problem. Or maybe the holidays are in January, and you have to improve the performance in spring or summer. That depends on the use of the building, but there is not a straightforward answer to shall I use glass, a lot of glass in buildings in New England? And no, I don't think it's the right answer, because it depends on a lot of factors. What is the use of the building? What is the schedule of the building? What are the days with sun in winter and in summer? So it depends on a lot of things, and that's why analyzing buildings, it's quite complicated, and you need experience. If you have been working on this in this area and on the construction field and on the building simulation for 30 years, without simulating anything, you can, okay, in Keen, with this area of windows, this kind of window with this solar heating coefficient and this U value, no way. You have to use something like that. But that comes from experience. If you are not experienced, and you are not, then you have to rely on software. But again, software is there is not a unique software that help you do anything. No, it doesn't exist. So you have to stick to what you know. And what do you know? Simple, basic building science. And it will always work. If you try to use a complicated software with thousands of parameters and you get the result, okay, this is the result. I submit it to my client and that's it. No, analyze the results by using simple, you say, okay, is it, is this balance between solar heat gains and solar heat losses accurate? So let's do something that you know that it's working, and then compare the basic knowledge to the complicated software. And by comparing these two things, you will get to know, okay, I can trust this software because with my rule of thumb, I agree that this is working. And then the complicated software confirm my first impression. And if it doesn't confirm your first impression, it's maybe because your first impression was wrong, or the complicated software is wrong. But we don't know, and it's quite difficult to find out.